This is a sound wave. It looks like a complicated mess, but when you listen to it, your ear somehow picks out individual notes. Your brain is doing something remarkable. It is breaking this single wave down into its constituent frequencies. The question is, can we teach mathematics to do the same thing? To do this mathematically, we need to express the complex wave as a sum of simpler building blocks. But this brings up a subtle question. Which type of pure frequency wave should we use to decompose the original signal? We could use square waves, triangular waves, sine waves, or cosine waves, all of which can have the same frequency and each of which consists of a single frequency. We can think of these pure waves as fundamental building blocks, or what mathematicians call a basis. The building blocks we choose must fulfill certain criteria. First, we must be able to reconstruct the original sound entirely out of them. Second, they must be independent, meaning no single building block can be built out of the others. Otherwise, they would be redundant. Now we are ready to understand how we can find the frequency components of a signal. The mathematical trick to extract these frequencies is called a change of basis. To understand this concept, let's look at the hyperbola xy equals 1 and ask, what is its eccentricity? At first glance, it is difficult to deduce from the equation alone. However, if we simply rotate the coordinate axis by 45 degrees, the equation transforms beautifully, and the eccentricity becomes obvious. We haven't changed the shape itself, we've merely changed our perspective, our coordinate axis, to make the math easier. We will do exactly the same thing with the Fourier transform. Let's see exactly how this change of basis method works to transform an equation from one perspective to another. We'll take our hyperbola xy equals 1 and map it into the new space created by rotating the axes by 45 degrees. Here, I'm simply trying to visualize what a transformation looks like in terms of a change of basis. In a 2D plane, we only need 2 basis vectors. In 3D space, we need 3. But when we move into frequency space, we are dealing with infinitely many dimensions, which means we need an infinite number of basis vectors. For example, let's look at sine waves. 2 sine waves are mathematically independent as long as their frequencies are different. And since frequency is a continuous spectrum, we have an infinite number of distinct frequencies to serve as our basis. When a signal is initially represented in the time domain, its basis is the Dirac delta function at every single instant in time. Mathematically, this means the signal g of t is just the integral of g of tau multiplied by delta of t minus tau d tau. To switch our perspective, we now need to find an appropriate basis in the frequency domain. To choose the basis in the frequency domain, we first need to decide what fundamental signal type we want to use. We could choose square waves, sine waves, cosine waves, and so on. Then, we need to find a set of basis vectors corresponding to that fundamental wave type. Let's say we choose square waves, meaning we want to express our original signal as a combination of square waves of different frequencies. We need to find an appropriate set of basis vectors for the frequency space, and that's exactly what the Walsh-Hadamard transform does. However, sine and cosine waves are a much more natural choice for studying sound and light. Individually, using only sines or only cosines isn't enough to capture every possible phase of a signal, but combining them works perfectly. To smoothly decompose a signal into both sine and cosine components, we use the complex exponential as our basis function, driven by Euler's famous formula. we assign one of these complex exponential basis functions to every single frequency f. Remember the projection concept from earlier? For it to work properly, our basis functions must be orthogonal. And indeed they are. If you take the integral of e to the power of j2 pi f1t multiplied by e to the power of j2 pi f2t over all time, it equals the delta function delta of f1 minus f2. This means projecting any basis function onto a different one always yields exactly 0, proving they are perfectly independent. We can also verify this with Parseval's theorem, which states that the total energy of the signal in the time domain must equal its total energy in the frequency domain. This energy match guarantees that we haven't missed a single frequency component. With their independence established, extracting specific frequency components becomes as simple as casting a shadow. Suppose we have a discrete signal made of several frequencies. To isolate just one specific coefficient, a sub I, we multiply the entire signal by e to the power of minus j2 pi f sub it and integrate. Because the basis functions are orthogonal, every cross term completely vanishes, leaving only the amplitude a sub I behind. When we generalize this logic to continuous signals, we arrive at the formal definition. The forward Fourier transform pulls the frequencies out of time, and the inverse Fourier transform reconstructs the original signal from those frequencies. Together, these two equations form the legendary Fourier transform pair. We can visualize the Fourier transform in another way by starting with a much simpler case, periodic signals. If a signal repeats perfectly with a period, t, we don't need a continuous transform. Instead, we can represent it as a sum of complex exponentials at discrete frequencies. This is the classic Fourier series, since the allowed frequencies are restricted to integer multiples of 1 over t. The frequency spectrum consists of a set of isolated spikes. But here comes the brilliant insight. What if the signal doesn't repeat? We can imagine it as a periodic signal whose period keeps getting larger and larger. As we stretch the period, t, toward infinity, the spacing between the allowed frequencies, 1 over t, shrinks toward 0. The discrete frequency spikes become packed closer and closer together until they form a continuous distribution of frequencies. If we compare signals in the time domain to their frequency domain pairs, a beautiful pattern emerges. A signal that is tightly squeezed in time is widely spread out in frequency, and vice versa. This is not a coincidence. It is a direct consequence of the time-frequency uncertainty principle, the exact same mathematics that drives Heisenberg's uncertainty principle in quantum physics. It proves that no signal can ever be perfectly localized in both time and frequency simultaneously. But to use this math in the real world, we run into a major roadblock. Computers cannot handle continuous infinity or perform perfect integrals over all time. Instead, they must capture discrete snapshots of the wave. To avoid corrupting the data, we must sample the wave at least twice as fast as its highest frequency, a rule known as the Nyquist-Shannon sampling theorem. Once safely sampled, we can calculate the discrete Fourier transform. But there's a catch. Computing this transform directly for n samples takes n squared operations. For modern audio or video, that is agonizingly slow. The solution: a clever algorithmic trick called the fast Fourier transform, or FFT. By breaking the problem down recursively, the FFT computes the exact same result in only n log n operations, transforming an impossibly slow calculation into something that can run effortlessly in real time.